Okay, let's run through the three problems for the Newton's Laws of Motion lab. The first lab setup has your cart with the little plastic wheels on it, with the string going down to a few quarters. Don't make this very heavy or it's going to go sailing way too fast. 20 grams would be more than enough. 250 grams, say, for your wooden cart. We'll use F equals ma to calculate the theoretical acceleration. We now know that this weight is equal to mg, 0.196 newtons. That's the force that's going to make the whole system accelerate. The mass of the system, 0.270 kilograms times the acceleration. I get 0.726 meters per second squared, and that's theoretical. Now for the experiment. You let the cart go. Maybe you've got a nice sized table. Make sure it's level. You have a distance of, say, 70 centimeters. Make sure you have enough room for the weight to fall. It's got to fall 70 centimeters then, in a time of 1.72 seconds. Just use distance equals 1/2 at squared. And that acceleration, 0.473 meters per second squared, is the experimental. So how do we know we have any friction? Well, the theoretical is larger than the experimental. This includes the friction. Where do you think that goes in the diagram? A good bit of the friction comes from the wheels with the straws and the wooden axles. That's going to be where most of your friction comes from. Some of it's going to come from this pulley. I'm going to ignore that and just ascribe it all to here. I'll start over with F equals ma. This weight pulls the system forward. That friction pulls it backwards. So we write forces forward minus forces backwards. Mass of the system, both objects. Now, which acceleration do you want to use? It's the experimental, because that has friction in reality. This is theory without friction. And of course, we know the weight, and now we can calculate the friction. And that's the force of friction in newtons. Compare that number to the weight pulling it forward. It's kind of hard to see at first, but it's about 1/3 of that. So as small as that number looks, it is a fair amount of friction for this problem. And this is what explains the theoretical acceleration dropping that low for the experimental. All right, so let's say we go to problem 2. You have the 20 grams hanging, you got the 250 grams. What angle would give you the equilibrium? We know the weight is 0.196 newtons. The weight of the cart is 2.45 newtons, and because it's tilted at an angle, we can break this weight into two components, and that component is pulling the cart back. That's pulling it forward. If we're in equilibrium, these two forces have to be equal. Make sure we don't confuse the weights. The force pulling it forward equals the force pulling it backwards. That parallel component is the weight of the cart times sine of the angle. Now we solve for the angle. Now this only gives us an angle of 4.6 degrees. I would suggest that if you do the lab, you make this much larger, like 40 or 60 grams. So we've calculated the equilibrium angle to be 4.6 degrees. I'll just keep it up here for reference. And now we're going to tilt the ramp to maybe 12 degrees. You don't need to try to match this height to a certain angle. Just get the thing up and measure the angle. Now we can use Newton's second law to determine the theoretical acceleration. First, let's calculate the force going down the plane. I get 0.509 newtons by taking 2.45 times the sine of 12 degrees. Now that force is bigger than this force. So I'm going to say this is the forward direction. I'll take the forward force minus the backward force and solve for the acceleration. That's 1.16 meters per second squared, and it's theoretical. Now, unless you tilt your whole table, you're using the little board that I gave you. That's not a lot of room to work with. So we're only going to have 0.3 meters for it to take a run and then we'll be able to calculate the experimental acceleration. You might want to slow motion video this. Let's say you get 0.95 seconds for this run. What would be the experimental acceleration? Again, use distance equals 1/2 at squared. We get an experimental acceleration of 0.66 meters per second squared. Now, of course, your data is going to be all different, but it should show us that we have some serious friction in this lab. We'll keep the values up here and tackle the friction. So we saw that this force was bigger than this force, making the cart go downhill. So the friction is going to have to go up the hill. Now there's going to be some friction in the pulley, but again, I think most of it's in the wheels. We're going to ascribe the friction to be at the cart. How do I handle the forces? Since this force is bigger than that force and the cart went downhill, I'll say this direction is positive and this direction is negative. So I have the force forward minus the force backwards minus my force of friction equals the mass of the system times acceleration. But which one? It'll have to be the one that would include friction. That would be the experimental. 0.66 meters per second squared. And I get 0.135 newtons of friction. Again, even though that seems like a small number, it's fairly significant to compare to the forces we're using. Depending on your equipment, you could get a much different number. And the last experiment is called the Atwood's machine. It's just two masses hanging by the string over a pulley. You're going to need narrow objects if these weights are going to pass each other without colliding. I got good results when these masses were not that different from each other. Don't use masses of just say 20 or 30 grams. Try to use a couple 100 grams on each side. The D-cell battery works pretty good for me. Don't assume that they're both the same mass. Put them on the scale and measure them, and then add a couple of quarters to one side. If there's too big a difference in your masses, it's going to fall so quick, you'll have a hard time getting a good time. Mass times acceleration, done in kilograms, and we get 2.744 newtons. And we get 2.646 newtons on this side. So we can see that this will fall down while that goes up. We'll say this is the forward direction. That's the backwards direction. F equals ma. The force forward minus the force backwards equals the mass of the system times the acceleration. And there's my acceleration, 0.178 meters per second squared, theoretical. Now we run the experiment. The weight falls 90 centimeters. You know, you don't have to work on a table. You can make this pretty high. You can hang this from something high up and have that weight fall a long way. I gave you plenty of strength. So let's say it falls 90 centimeters in a time of 3.54 seconds. Let's go calculate the experimental acceleration. And we get an experimental of 0.144 meters per second squared. And yeah, it should be smaller than the theoretical because we do have some friction in here. Let's tackle that. Hey, there's no wheels on any cart. Where's the friction then? It's got to be in the pulley. If the weight goes this way and the pulley rotates that way, the friction's the other way. So I have my force forward, and I have two forces backwards. Forward and the backwards. Mass of the system, and we'll multiply by the experimental acceleration. I get a fairly small force of friction. We're hoping that's what's going to happen with the Atwood's machine because you don't have the wheels creating friction. It may just be the pulley. And it would be good to take a look at this force in comparison not to these forces, but to the difference in those forces. So we can see that this friction force is pretty small compared to the difference in these forces. So just choose one of those three labs to build and test. All right, just one more thing. Kids are asking me, how do you find the tension in the rope? The tension in the rope is the force that pulls this cart forward, but it also holds the hanging mass backwards. If we look at this whole system, We have 4.9 newtons pulling forward. We have tension pulling backwards and a tension pulling forwards. What would happen to these two forces if we use them in F equals ma? That would be a forward force. That would be a forward force. And this would be a backwards force. They would make the mass of the system accelerate. I'm sure you can see that the tensions will cancel. These are called internal forces. An internal force cannot accelerate the entire system. Do the math and we get 1.633 meters per second squared for this system. So how do I find the tension? I have to isolate one of the parts of the system. I have to break the system up. When I do that, this now becomes an outside force or an external force to this system. What makes that cart accelerate? Just the tension. The mass of the system is now just the mass of that cart. And it's accelerating at 1.633 meters per second squared. So we can calculate a tension of 4.083 newtons. Could we have also used this object as my system to calculate the tension? By isolating this part, I can now say I have two external forces acting on this mass. Start with F equals ma. The force forward minus the force backwards equals the mass times the acceleration. I get 4.083 newtons. Hey, I'm getting the same thing. Hey, that tells us something. The tension is the same across a frictionless massless pulley, otherwise known as an ideal pulley. Now, after you do the lab, make sure you practice all this on the worksheet.